Hello students, hope you are well. All well. In this class I should discuss about colligative property of solution. Colligative property is a very important property of the solution which depend upon the number of solute particle, depend on number of solute particle but not on their nature. But not on their nature. As it is a crash course class, so taking into mind of all kinds of questions which might come into the competitive level, I'll discuss all this now. The following properties are coming under colligative properties. The property coming under colligative properties are: number 1, lowering of vapor pressure. Vp means vapor pressure. Number 2, elevation of boiling point. Number 3, depression of freezing point. Number 4, osmotic pressure. Look at here, I have taken only water, which is solvent, and I have taken sugar solution. So vapor pressure is the pressure at which the liquid starts boiling at a particular temperature. In case of solvent, vapor pressure is equal to 1 atm or 76 mm of mercury. Suppose it is 1 atm. At that pressure, water starts boils. Okay. Now, in case suppose it is a solvent line, it is a solution line. AB stand for solvent line, CD stand for solution line. From the graph, it is evident that solution has a lower vapor pressure than that of the solvent. So when some non-volatile solute is dissolved in a solvent, vapor pressure of the solution is lowered. Now, as it is colligative property, so I can say that more number of solute particles, solute molecules, less will be vapor pressure. I have taken two solutions. One is 1 molar glucose and it is also 1 molar urea. In both cases, number of solute molecules are same because it is equal to 1 molar means 1 moles of solute, that is 6.023 into 10 to the power 23 molecules. It can be glucose as well as urea also. Vapor pressure of 1 molar glucose solution and 1 molar urea solution is same. From that I can say that colligative property depending upon the number of solute particle. Instead of 1 molar, if I take 2 molar glucose, you will see that vapor pressure of 2 molar glucose less than vapor pressure for 1 molar glucose. More the concentration of the solution, less will be vapor pressure. Suppose it is a solvent line, AB stand for the solvent line, CD stand for 1 molar solution line, EF will be 2 molar solution line. EF is lower than 1 molar. Hence, more the concentration, less will be the vapor pressure. Vapor pressure for 1 molar is over here, 2 molar is much lower. So, more the concentration, less will be the vapor pressure of the solution. This is first part. But if I take 1 molar solution only, in this case I have taken 1 molar urea, 1 molar NaCl, 1 molar MgCl2, 1 molar AlCl3. In all the cases, concentration is same. So obviously, colligative property, that means vapor pressure lowering, will be same in both the cases, in all cases. But contrary to the fact, if the solute particle undergo association or dissociation, number of particle changes, hence observed value what is experimentally observed will differ from expected value derived from the formula. Suppose we have taken 1 molar NaCl and 1 molar urea. In 1 molar urea and 1 molar NaCl, number of particles are not same. NaCl totally break up to Na plus and Cl minus. So number of solute particle for NaCl is 2 mole ion. For MgCl2 it is equal to 3 mole ion. For AlCl3 it is 4 mole ion. More the number of solute particle, less will be the vapor pressure of the solution. So order of vapor pressure of such solutions will be in the order, vapor pressure of solution will be in the order P of AlCl3 will be less than P means vapor pressure, MgCl2, less than P of NaCl, less than P of glucose solution. One more property where the same relationship found, that is the case of freezing point of the solution. More the number of particle, less will be the freezing point of the solution. More the number of particle, less will be freezing point of the solutions. Hence freezing point of the solution will be in the order TF, that means freezing point of TF of AlCl3 less than TF of MgCl2, which is less than TF of NaCl, which is less than TF of glucose. Okay, followed? Now Van Top used a factor I which account for the ratio between change in vapor pressure observed to that of expected, that is denoted by a factor that is I. So Van Top factor I equals to Van Top factor I equals to delta P observed over delta P expected. Delta P means change in vapor pressure observed by expected is equal to delta TB observed over delta TB expected equal to delta TF observed over delta TF expected over pi observed by pi expected. In case of molecular weight, this relationship is reversed. So molecular weight expected over molecular weight observed. Molecular weight I am writing in some other color such that the difference you can easily look. It is easily look into your eyes, that is molecular weight, the relationship is reversed. So I is the, what is I? I equals to number of solute molecules, solute particles, it can be molecule as well as ions, at equilibrium over initial concentration, over initial moles. Okay, let us discuss these things now. Suppose in case of NaCl, it break up to Na plus Cl minus. So initial mole is 1. If I take 1 molar, moles at equilibrium will be what? Moles at equilibrium, that is ions. Mole ion at equilibrium will be 1 plus 1, 2. Hence I will be is equal to 2 by 1, that is 2. For MgCl2, similarly, I equals to 3. For AlCl3, I equals to 4. So more the value of I, more will be the observed value than expected value. Hence, observed lowering of vapor pressure will be more than that of the expected lowering. Depression in freezing point will be more than it is expected. Elevation of boiling point will be more than expected. And molecular weight of LCl3 will be less than observed. Because you know, I equals to what I have written? I equals to I have written molecular weight expected by observed. So molecular weight observed will be molecular weight expected by I. For dissociation, I greater than 1, hence molecular weight observed less than molecular weight expected. This is very, very important. Now, if the solute particle doesn't dissociate completely, I will derive a relationship, show you a relationship between the Van 't Hoff factor with degree of dissociation. Look at here. Think of the case, a substance AB, ABN. It breaks up to Na plus it will breaks up to An plus Nb minus. Okay, so how to find out? Total number of particles is equal to what? N plus 1 is the total number of particles. It is 1, it is n. That is total number of particles, n plus 1. So it is 1 minus alpha. So it will be alpha plus n alpha. Because for 1 mole, it form 1 mole ion, it form n mole ion. Achha, see, it is 1, it is n. Total n plus 1 particles are there. So I equals to what? 1 minus alpha plus, what are the total number of particles? It is n here 1, n plus 1 into alpha. This is the I value. Achha, suppose it is the, you may not come, you may find it difficulty as it is written n over here. Think of the case of this one. Okay, suppose MgCl2, it break up this way, so Mg2 plus 2Cl minus. If I consider it doesn't break up completely, in this case 1 mole gives you 1 plus 2, 3 mole ion. So write 1 minus alpha, alpha is the degree of dissociation, plus total number of mole ion, that is how much? 3 3 into alpha. So total become what? Is equal to 1 plus 2 alpha. Okay, so if a substance break up into n plus 1 ions, in this case I is equal to total number of particles will be what? 1 minus alpha plus n alpha plus alpha, that is 1 plus n alpha. Okay, if n is equal to what is called n is equal to 2, so it will be what? 1 plus 2 alpha. N is equal to 3, 1 plus 3 alpha, etc. Or generally, suppose if I write it this way, suppose it is a substance break up into n numbers of ions. Suppose it is AB2, AB3, it break up into A3 plus 3B minus. So 1 minus alpha gives you what? What are number of the particles? 1 plus 3, that is 4. So it will be 4 mole ions, so 1 minus alpha plus 4 alpha. I will be what? 1 minus alpha plus 4 alpha by 1. Initial concentration I is equal to what? 1 plus 3 alpha. When it gives 4 mole ion. If it gives 5 mole ion for 4 mole ions. For 6 mole ions, what it will be? I is equal to what? 1 plus 5 alpha. For 3 mole ion, what it will be? I is equal to 1 plus 2 alpha. Is it clear? So it will be 1 minus alpha plus total number of mole ion it is break up, as it is 1 plus 3 will be 4 alpha. So become 1 plus 3 alpha as it is written over here. So whatever be the number of mole ion will be 1 less than that into alpha. 1 plus that value into alpha. So if it is 3 means it break up into 4 mole ions. 5 means it break up into 6 mole ion. 3 means it break up into 2 means it break up into 3 mole ion. In this way, I can find out the relationship between I, which is equal to total number of molecules at equilibrium by initial concentration. In this case, what it will be? So I is equal to what? If a substance break up into n number of mole ion, what it will be? 1 plus n minus 1 into alpha by 1. For a substance broken from n mole ions. Ions at equilibrium. So in this case, it will be I minus 1 by n minus 1 into alpha is the relationship between I and degree of dissociation. I is Van 't Hoff factor, alpha is the degree of dissociation. When n is equal to 2, as for example NaCl like cases, I minus 1 by 2 minus 1 is equal to alpha. For MgCl2, it breaks up into 3 mole ion, so n is equal to 3. So I minus 1 by n is 3, 3 minus 1 by 2 is equal to alpha. For 4, I minus 1 by 3. In this way, we can find out the relationship between the degree of dissociation and Van 't Hoff factor. Now, what I want to tell you, if it undergo dissociation, in this case, number of particles increases, though. Hence, what happen? Observed molar mass will be less than expected molar mass. So, I is equal to what you have written? Molecular weight expected by molecular weight observed. Okay. Now suppose in the case of n is equal to 2, a substance, a solute form 2 mole ion. In this case, I is equal to what? I is equal to, we have written as 1 plus n minus 1 into alpha for dissociation. When n is equal to 2, I is equal to what? 1 plus alpha. So molecular weight expected over molecular weight observed is equal to 1 plus alpha. When n is 2, so molecular weight observed is molecular weight expected divided by 1 plus alpha, as 1 plus alpha is greater than 1, so molecular weight observed will be less than molecular weight expected. As 1 plus alpha is greater than 1, molecular weight observed will be less than molecular weight expected. So due to dissociation, molecular weight decreases. Now, in case of association, number of particles decreases. Hence, observed value of molar mass will be more than expected molar mass. Look at the case of this. Suppose it is associated as dimer in benzene solution, forming this. If alpha be the degree of association, so for every 2 mole 1 mole is formed. So if it is 1 minus alpha, it become alpha by 2. I is equal to what? Total numbers of solute at equilibrium, 1 minus alpha plus alpha by 2, that is 1 minus alpha by 2. Now I equals to what? I equals to molecular weight expected by molecular weight observed molecular weight observed will be what? Molecular weight expected by I. I value is what? I have got as molecular weight expected over 1 minus alpha by 2. If it undergo complete association, in this case alpha is equal to 1. For complete association to form dimer, for complete association to form dimer, alpha will be 1. So in this case molecular weight expected by 1 minus 1 by 2, that is half, is equal to 2 into expected, is equal to 2 into 60, that is 120. So observed molecular weight of acetic acid in benzene is double that of actual value, hence it's found out to be true. If in this case not complete association takes place, in this case the value will be in between 60 and 120 depending upon degree of association. More it will be associated, more will be your molar mass. More it will be dissociated, less will be your molar mass. So hope you have followed this part up to this today. Next day we should discuss the other part of it.